Hey everyone, and welcome back for another deep dive. Today, we're going to be talking about something pretty amazing.
Yeah,
Um,
it's pretty wild.
it really is, and it's something that a lot of people are talking about these days, especially after the news came out this month,
Yeah, in January.
in January exactly,
Yeah.
about China and their artificial sun.
Mm-hmm.
So that's what we're going to be deep diving into today, and I've got an expert here with me to break down exactly what's going on, because I'll be honest, I don't fully get it.
Sure.
But yeah, so what can you tell everybody about, what this is all about with this artificial sun? What have we heard so far?
Well, so the term artificial sun is really just a kind of a catchy name that people have given to this new advancement in nuclear fusion, and specifically, it's about the experimental advanced superconducting tokamak, which is known as EAST, and it's a Chinese project that has been in development for a number of years now.
I see. Okay.
And just this month, they hit a really important milestone.
Okay, so we're talking about nuclear fusion, which I guess, people hear the word nuclear and they kind of, freak out a little bit.
Yeah, and I think it's important to differentiate between, nuclear fission,
Mhm.
which is what a lot of people think about when they think about nuclear power and nuclear fusion, because they are very different.
Okay.
So when we talk about nuclear fission, we're talking about the process of splitting atoms, and that's how we generate energy in traditional nuclear power plants.
Right.
With fusion, we're talking about taking two atoms and forcing them together, basically fusing them.
Oh, okay.
And when that happens, you get a release of energy, and that is what powers the sun.
Oh, so what they're doing in China with this east
Right.
is they're basically trying to recreate what the sun does naturally but on Earth.
Yeah, in a controlled environment. And it's been really challenging to do that because you have to generate extremely high temperatures and pressures to be able to force those atoms together. And
Yeah, it sounds really hard.
it is.
But well,
But it's the holy grail of energy in a lot of ways because,
yeah. Why is that? Like, what's so special about fusion if we were able to pull it off?
well, one of the biggest advantages of fusion is that it produces very little radioactive waste
Okay.
compared to fission, which produces a lot of long-lived radioactive waste that we have to figure out what to do with.
Right. That's been a huge problem with nuclear energy up to this point.
Exactly. And it's also a very efficient process.
Rip.
A small amount of fuel can produce a tremendous amount of energy.
Got it.
So it's a very clean and efficient form of energy if we can make it work.
I see. Okay. So that's why everyone's so excited about fusion and why China is pouring so much money into this research.
Exactly.
So let's talk a little bit about this EAST device you mentioned earlier, this
Mhm.
experimental advanced superconducting tokamak.
Mhm.
Can you kind of explain what that is and how it works?
Yeah, so a tokamak is basically a donut-shaped device.
Mm.
And the way it works is it uses magnetic fields to contain the plasma. And plasma is basically a superheated gas where the electrons have been stripped from the atoms. So you have this kind of a soup of charged particles.
Oh, way.
And it's very hot.
So we're talking about like millions of degrees, right?
Millions of degrees, yes, hotter than the core of the sun.
Wow. So they've created this super powerful magnetic field that can hold this unbelievably hot plasma.
Right. And the reason they need to do that is because if the plasma touches the walls of the reactor,
Oh,
it will melt.
that doesn't sound good.
Yeah, it'll basically destroy the reactor.
Okay, so it's a very delicate balancing act,
It is.
keeping this incredibly hot material contained without letting it, touch anything.
Right.
Wow, it's amazing that they can even do that.
It's an incredible feat of engineering.
So can you tell everyone what exactly is this big milestone that they just hit?
Yeah, so they were able to sustain a plasma at 70 million degrees Celsius for 1,056 seconds, which is about 17 and a half minutes.
Whoa. Okay, hold on.
17 minutes, 70 million degrees.
Celsius.
Yes.
That's insane. Like,
My
how is
God.
that even possible?
Well, it's taken a lot of years of research and development to get to this point.
Yeah.
They've been constantly refining the design of the reactor, improving the magnetic fields, and developing new materials to be able to withstand these extreme conditions.
So 17 minutes might not sound like a long time, but in the world of fusion research,
Mm-hmm.
that's a huge deal, right?
It's a huge deal because it shows that they're making progress toward being able to sustain a fusion reaction for a long enough period of time to actually produce energy.
I see. Okay.
And that's really the ultimate
Yeah.
goal, is to be able to create a self-sustaining fusion reaction that can produce more energy than it takes to create.
So this is like a major step towards that.
It is a major
So,
step.
so we've got this artificial sun. We've got this, incredible breakthrough in China.
Mm-hmm.
But I got to ask, like, what does this actually mean for the average person?
Well, it's still very early stages. As I said, it's going to be a long time before we see fusion power plants powering our homes and businesses. But this is a very promising sign that we are on the right track.
Okay.
And it gives us hope that we might be able to solve some of the world's energy problems.
So you're saying this could be a game changer down the line.
It could be a game changer, yeah.
All right, well, let's take a quick break. And when we come back, we'll dive even deeper into the potential of fusion power and what it could mean for the future.
Sounds good. I think it's important to acknowledge just how complex this technology really is.
Oh, yeah, absolutely. I mean, we've been throwing around terms like plasma and tokamaks and superconductors, but I'm sure a lot of people are still scratching their heads.
Right. And even for those of us who've been following this field for a while, it's still mind-boggling to think about what they're trying to achieve.
So break it down for us. What are the biggest challenges standing in the way of making fusion power a reality?
Well, we've talked about the need to create and contain this superheated plasma at millions of degrees Celsius, hotter than the sun's core.
Right, and doing that for 17 minutes is a huge accomplishment. But what's the next step?
The next step is to extend that duration significantly to hours, days, even weeks at a time.
Okay, so it's not just about creating those conditions for a short burst, but maintaining them for extended periods.
Exactly. And that presents a whole host of challenges.
Like what?
Well, for one, plasma is incredibly unstable. It wants to wriggle free from those magnetic fields, and even the slightest instability can disrupt the entire reaction.
So it's like trying to hold a wriggling snake in a straight line.
That's a pretty good analogy.
Yeah.
And then there's the issue of the materials used in these reactors. They need to withstand those incredibly high temperatures and intense radiation without degrading. It's like trying to find a material that won't melt in a volcano.
Right, because if the reactor walls fail, the whole thing could go haywire, and I'm guessing that's not a good thing.
It would be a major setback, to say the least.
So it sounds like we're talking about not just one scientific breakthrough, but a series of them across multiple disciplines.
Precisely. You've got plasma physics, material science, engineering, computer modeling, all coming together to tackle this challenge.
It's a massive undertaking.
Yeah.
But let's assume for a moment that they do overcome these hurdles. What could a future powered by fusion look like?
Well, the most immediate impact would be on our energy production. We could say goodbye to fossil fuels and all the environmental damage they cause.
No more greenhouse gases, no more air pollution, a cleaner, healthier planet.
Exactly. And with a virtually limitless source of energy, we could power everything from our homes and businesses to transportation systems and industries without worrying about running out.
It sounds almost too good to be true. What about the cost? I imagine building these fusion power plants must be incredibly expensive.
The initial investment would certainly be substantial, but in the long run, fusion power has the potential to be much cheaper than fossil fuels.
How so?
Well, the fuel for fusion is derived from seawater, which is abundant and readily available. And once a fusion reaction is initiated, it can sustain itself, releasing enormous amounts of energy with very little input.
So it's like a self-powering system that runs on seawater.
Essentially, yes. And because it doesn't produce greenhouse gases or long-lived radioactive waste, the environmental costs would be minimal.
Okay, now I'm really starting to see the appeal. But we've been focusing a lot on the large-scale projects like EAST and ITER. What about those smaller startups you mentioned earlier, the ones developing compact fusion reactors?
Ah, yes, the underdogs of the fusion race. They're taking a slightly different approach, focusing on smaller, more modular reactors that can be deployed more quickly and cost-effectively.
You mentioned they're using high-temperature superconductors.
Hmm.
Can you remind me what those are and why they're so important for these smaller reactors?
Sure. High-temperature superconductors are materials that can conduct electricity with zero resistance, but only at extremely low temperatures.
Right, I remember you saying it was a bit of a catch. So they need to be super cold to work their magic.
Exactly. But even though they need to be kept very cold, these new superconductors can operate at higher temperatures than traditional ones, making them more practical for use in fusion reactors.
So they're not exactly room temperature, but getting closer.
Right, and that ability to conduct electricity with zero resistance allows for much stronger magnetic fields, which are essential for containing the plasma in those smaller reactors.
So it's like squeezing the same power into a smaller package.
Exactly. And these startups believe this approach could lead to faster commercialization, potentially bringing fusion power to market much sooner than those large-scale projects.
It's like a David versus Goliath scenario, with these small startups challenging the giants of fusion research.
It is. And it's exciting to see so many different approaches being pursued because it increases our chances of success.
It really highlights the global interest in investment in making fusion a reality. But amidst all this excitement, it's important to consider the potential downsides as well.
Absolutely. No technology is without its risks and challenges.
So, what are some of the potential drawbacks or concerns we need to be aware of when it comes to fusion power?
Welcome back to our deep dive on fusion power, where we've been exploring the incredible advancements and the potential of this, I guess, almost like sci-fi technology.
It really does feel like science fiction, doesn't it?
It does.
This idea that we could harness the power of the sun here on Earth.
Exactly. But as we were just discussing, there are potential downsides to consider too. So let's talk about those. What are some of the concerns people have raised about fusion power?
Well, one concern that often comes up is the issue of radioactive waste.
I thought fusion was supposed to be clean, no waste.
It's cleaner than fission, for sure, but it's not completely waste-free.
Oh, okay. So there's still some radioactive byproduct.
Yes, but it's important to understand that the type and amount of waste generated by fusion are significantly different from what we see with traditional nuclear power plants.
Okay, can you elaborate on that? What's the difference? Sure. Fusion reactions produce a type of radioactive waste that has a much shorter half-life. That means it decays to safe levels much faster, sometimes within years or even decades, compared to the long-lived waste from fission that can remain hazardous for thousands of years.
Okay, so less waste and the waste is less dangerous.
Right. However, even though the waste is less problematic, it still needs to be managed responsibly. And developing safe and efficient waste disposal methods is a crucial part of making fusion power a viable option in the long run.
That makes sense. So waste management is one challenge. Are there any other potential downsides or risks we should be thinking about?
Well, another concern is the sheer complexity and cost of building and operating these fusion reactors. The technology is still in its early stages, and it requires incredibly sophisticated equipment, specialized materials, and a highly skilled workforce.
So it's not just about the initial investment in research and development, but also the ongoing costs of maintaining and operating these power plants.
Exactly, and let's not forget the issue of safety. Fusion reactions involve incredibly high temperatures and pressures. Ensuring the safety and reliability of these reactors is paramount. We need to develop robust safety protocols and systems to prevent accidents and contain any potential releases of radioactive material.
Right, because a fusion power plant meltdown is not something anyone wants to imagine.
Exactly. So while fusion holds incredible promise, it's not a silver bullet solution. We need to approach it with a realistic understanding of both its potential and its challenges.
Okay, so we've talked about the potential downsides,
Hmm.
waste management, complexity and cost, and safety concerns. But let's shift gears now and focus on the bigger picture. Assuming we do manage to overcome these challenges, how could fusion power reshape our world?
It's really mind-boggling to think about the potential ripple effects from the geopolitical landscape to the global economy and even our daily lives.
Let's start with geopolitics. How could fusion energy impact international relations?
Well, as we discussed earlier, much of the current geopolitical landscape is shaped by the uneven distribution of fossil fuels. Countries with abundant oil and gas reserves wield considerable power and influence. Fusion has the potential to disrupt this dynamic.
So countries that have traditionally been reliant on energy imports could become more self-sufficient.
Exactly. And that shift in energy production could lead to a redistribution of power and influence on the global stage. We might see new alliances emerge as countries collaborate on fusion research and development, sharing knowledge and resources.
It's interesting to think about how this could potentially reduce those geopolitical tensions that often arise from competition over energy resources.
Exactly. And what about the economic implications? Imagine a world where energy is abundant and cheap, thanks to fusion power. It could revolutionize industries, from manufacturing and transportation to agriculture and technology.
I could see how that would create countless new opportunities for innovation and economic growth.
Hmm.
We might see entirely new industries emerge, focused on developing and deploying fusion technology and its applications.
Absolutely. And the reduced cost of energy could make existing industries more competitive and efficient, leading to lower prices for consumers and a higher standard of living for many people around the world.
But of course, as we mentioned earlier, this transition wouldn't be without its challenges. We need to make sure that the benefits of fusion power are shared equitably and that we manage the economic disruption carefully to avoid creating new inequalities.
I agree. It's crucial to approach this transition thoughtfully, ensuring that everyone benefits from the cleaner, cheaper energy that fusion could provide.
Now, let's bring it down to a more personal level. How could fusion power impact our everyday lives? What could a fusion-powered future look like for the average person?
Imagine a world where your home is powered by a clean, reliable, and affordable energy source, where you can charge your electric car knowing that the electricity comes from a sustainable and environmentally friendly process.
No more worrying about rising energy bills or the carbon footprint of our energy consumption.
Precisely. And beyond our homes, we might see fusion power transforming transportation systems, leading to faster and more efficient trains, ships, and even airplanes, all powered by this clean and abundant energy source.
And who knows, maybe one day we'll even see fusion-powered spacecraft exploring the cosmos.
It's certainly within the realm of possibility, but even without venturing into space, the implications for our planet are profound. With fusion power, we could dramatically reduce our reliance on fossil fuels, mitigating the effects of climate change and creating a cleaner, healthier environment for generations to come.
It's a truly inspiring vision of the future. But as we wrap up our deep dive today, I think it's important to acknowledge that the path to this fusion-powered future is not going to be easy. There are significant scientific, technological, and societal challenges to overcome.
That's right. We've discussed some of those challenges today, and there are likely others that we haven't even anticipated yet. But despite the hurdles, the potential rewards are so great, so transformative that the journey is worth taking.
This has been an incredible exploration of fusion power, from the basic science to the complex challenges and the inspiring vision of what the future might hold. And I want to thank you for sharing your expertise with us today and helping us to understand this complex and fascinating topic.
It's been a pleasure, and I hope that our conversation today has inspired you to learn more about fusion power and to engage in the conversation about how we can shape a future where this incredible technology benefits all of humanity.
That's a great point. This is a conversation that we all need to be a part of. So, thank you for joining us on this deep dive into the heart of the sun on Earth. And until next time, keep exploring, keep questioning, and keep imagining the possibilities of a fusion-powered future.